Now, there's a particular problem variety, a type of problem that is very useful, and it occurs in more places than at first blush you might think. And so we're going to take a look at that. We're going to find the function values of an angle. Now, we're going to assume that the point in the plane is a point on the line y equals negative 4x. Now, it can be any line that passes through the origin. Remember, this is y equals mx plus b, and b is equal to 0, so we know this line passes through the origin. And so this can be any line passing through the origin. I've just randomly selected y is equal to negative 4x. And we're going to assume in this problem that x is greater than 0. You don't need to assume x is greater than 0. You could, but you need to choose one or the other. Either x is greater than 0 or x is less than 0. We know that x is not allowed to equal 0 because we know that would correspond to the origin, and the value of p is not allowed to equal the origin or be the point of the origin. And so we're assuming in this case x is greater than 0. The problem would be very similar if we were to assume it to be less than 0. And so we have y is equal to negative 4x. That's a line passing through the origin. We're assuming x is greater than 0, and we're asked to find the exact values. We find all the values, the exact values, no decimal approximation. So if you have square roots, leave them as square roots. The exact values of the 6 trigonometric functions. Now, there's one key idea in all this, and that really is the primary thrust of this, is this one really important key idea. So, here's the coordinate system. Here's the line y equals negative 4x approximately. Now, the question is, which point do we choose? And what I want to show you is, it doesn't matter. You may choose any point on this line. And now here's the argument. Call this P number 1. Call this P number 2. And I'm going to elevate this right angle, so that's the perpendicular. I'm going to elevate this perpendicular. And so if we use point number 1, we would be using x number 1, y number 1, and r number 1. On the other hand, if we use P2, we would be using x number 2, the larger value. We would be using y number 2, this larger value. And we would be using r number 2, this larger value. I'll put it down here, r number 2. Now, the key is these two triangles are similar. We know these angles are the same because these are parallel lines crossed by a transversal. We know these are right angles, and we know this angle is the same in both triangles. And so we know these are similar triangles. And so we know they are in proportion. And so if I were to say, just pick any two sides of this smaller triangle, I know, for example, y1 over r1. y1 is to r1, similarity, as y2 is to r2. So we know those are equal. And here's the point. Since it doesn't matter which one we pick, we know those are equal. Now, what is this? With respect to the smaller triangle, this is theta for both of them. It doesn't matter which triangle we pick. This is theta. We're choosing a quadrant 4 angle theta. Now I'm choosing, notice I'm choosing x to be greater than 0. You might say, well, if this line is passing through the origin, I can choose any point on this line. If I choose a point here, I am now violating this requirement. This x value is now negative. And so this extra requirement just tells you that, yes, I'm in quadrant 4. I am not in quadrant 2. So this extra requirement, you may be given either one or the other. If you're given x is greater than 0, then you know to choose the point on this end of the line. If we had been given x less than 0, then we would choose the point on this piece of the line. We just coincidentally happen to be given this piece, and so we know we're down here in quadrant 4. But look, with respect to the small triangle, I'll call this the red, the small triangle, we know sine of theta in that triangle is y1 over r1. So I'll do it this way. This is y1 over r1. But in the large outside blue triangle, that is also the same theta. So we know sine of theta is also equal to, it's y2 over r2. Right? So that's y2 over r2. But because they're similar triangles, we know those are equal to each other. So it doesn't matter which point we choose on the line, because they're always going to make similar triangles. We could choose a point number 3. There's point number 3, but that triangle is similar to these two also. And so x3 and y3 and r3, those are in proportion to the smaller triangles. It doesn't matter which one we pick. And there's nothing magic about y1 over r1. Pick any two triangles, any two sides of this small red triangle. Suppose I pick y1 over x1. Well, in the red triangle, that's y over x. That's tangent. So tangent of the small red triangle, tangent of theta, would be y1 over x1. But because of similar triangles, that's equal to y2 over x2. But that is tangent of theta in the large blue triangle. So tangent using the small red and tangent using the large blue, or for that matter, tangent using this very large green one. They're all the same because those are similar also, y3 over r3. It doesn't matter which triangle we pick, meaning it doesn't matter which point on the line we choose. All the function values are always equal. Since they all work, we can choose any point on the line we like. Since all of them work, we might as well choose an easy one. If the difficult ones work and the easy ones work, don't pick the difficult ones, pick the easy ones, because you get the same answers either way. And so for that purpose, for that reason, because we are free to choose any point we wish, we might as well choose an easy one. And that's why we're allowed to make the choice I'm going to demonstrate now. So that point really is the key argument for this problem. The rest of this is just filling in the details. Understanding that key idea is the main thrust of what's happening here. We are free to choose any point on the line so long as it makes this true and it makes this restriction true. Remember, this restriction must be given in the problem. If it is not given, then the problem cannot be done, not by you, but by anybody. So we need to draw our picture as we actually have it. We actually have y is equal to negative 4x. All right? Choose any point you want. What that means is this. Choose any x you want. It doesn't matter. Pick any x you want. X equal, so long as it's bigger than 0, you can pick anything you want. You might as well make it simple. Choose x equal to 1. That's about as easy as you're going to get. From this statement, this tells you what the y value is. I have chosen, let me move this around. I have chosen x equal 1 from this piece of it. Now, this has met this requirement. So yes, I've checked off that requirement, but we also have this condition to be met. And so we can compute the y value. That's negative 4 times 1 is negative 4. So I have y is equal to negative 4. So my point I've chosen is 1 comma negative 4. This is now the same as all the other problems we've done where you've been given a point. From this, you compute the value of r. I'm going to compute the value of r. Remember, r is equal to the square root of x squared plus y squared, which in this case is 1 squared plus negative 4 squared, square root, which is the square root of 17. Actually, it's positive or negative. Which one do we pick? We always use for r. R, we always choose the positive value. And so we know that r is equal to the square root of 17. Don't get the calculator. Don't write this as 4 point something, something, something. Leave it because you've been asked to give exact values. I'm telling you now, every time if you are asked to give exact values, you do not use a calculator to hit the square root button and get a decimal approximation. Do not do that. Use the exact value. Use the radical 17 symbol. Sometimes, I've had this happen with students in the past, and other instructors have had this experience, so I want to make sure this is squared away. That, as opposed to, let's see, let's go square root 17. I have 4.12310, 4.12310. I'm going to round that to 1, 2, 3, 1. I'm going to round that to 5 decimal places. This is rounded. If I round that to 5 decimal places, that's my number. Which of these is exact? I've had students in the past say this is exact. No, this is not exact. Suppose you round this to 4.1. I've had students say, no, this is an approximation, but this is exact. No, this is an approximation. That's an approximation. Anytime, I don't care which, when, where, whatever you're doing, anytime you round, if you use a rounding rule, anytime you round, this is no longer an exact value. The only way to express this for our purposes, the only way to express this as an exact value is here. If you reach for a calculator and mash the button, that's not going to be an exact value. For our purposes, the way you leave this is the square root of 17. So, that said, I'm going to get rid of all this. I'm going to get rid of all this. And all we need to do is now use the x, y, r definitions to fill in the values of the trigonometric functions. So we have sine of theta is y over r. That's going to be negative 4 over the square root of 17. You do not need to change it. You do not need to alter that. You do not need to make it look differently. That is good enough. Cosine theta is x over r. 1 over square root 17. Thanks for coming out. Tangent of theta is given by y over x. That's negative 4 over 1. You do not need to simplify. Now, it's not asking too much. Probably you wouldn't have any trouble writing that as negative 4. But as far as I'm concerned, that is perfect. That's just fine. You don't need to start picking at it. I've had students in the past do this. They see this, they say, no, I'm going to make it look better. And then they do this. They say this is equal to 4. And they put a box around it like they're proud of it. Do you see you made a mistake? You should have just let sleeping answers lie. If you're going to simplify this, then you stinking better do it right. This is not going to be correct. The safest thing is to don't pick at it. Just back away slowly and don't make eye contact. That answer is correct. It's correct enough. Once you have these three, the other three, just invert all the fractions. So cotangent theta is negative 1/4. Secant of theta is the reciprocal of this. That's the square root of 17. If you want to, you can even put it over 1. If you want to leave the 1 off, that's fine. If you want to put it on, that's fine. I don't care. So long as it's correct, I'm fine. But if you don't want to take any chances, write it this way, and that's fine by me. And then the last bit is cosecant, and that's negative square root 17 over 4. So, given any line that passes through the origin and given a specific restriction, then you should be able to find all the values of all 6 trig functions. Choose any x that you like, use that to find the associated y, and then you're off to the races.